So we can have, today we already have some examples of different languages. First, there was a proof of Lover's local lemma using probability counting. And then there was some kind of information theoretic proof, but just in some very special case. And maybe if you want, it's also a question, maybe we have to make a choice. I can try to explain the information theoretic proof in some more general case, almost close to the general case of Lover's local lemma, when we will have this simple bit counting argument instead of probabilities. Or I don't know how many of you were following previous talk and whether you want to hear something again on the same topic. So there are other examples not related to Lover's. So what do you think? Should we go into information proof of Lover's local lemma or not? Sure. So you like this lemma, and okay. But I'll still I will try to start with another more simple example, just kind of probabilistic argument. Oh, it even works. Great. Okay. Спасибо. Да. Okay, so I'll try to start with a very simple example. There is even a completely ridiculous one, but still it's funny. So let's prove that there are infinitely many prime numbers. Now it's also kind of combinatorial counting, but let me explain this argument in complexity form. So let's prove by contradiction. Imagine that there are only finitely many prime numbers. Then every number x can be represented as some product Pn, no, Kn. So x can be described by the string of n bit. N is some fixed things, but the k's are of course different for different x's. So to specify x, we can specify these numbers. So x normally, if we use normal binary notation, then it needs that many bits. And then we can, instead of this, we can specify separately each of them, each of these keys. And then we need this number of bits. And of course, we need also some kind of separator things. So let's be generous and say we use all of this number of bits. But also, of course, all ki are at most log of x. So in general, we get O of n log x bits. And so this is much less than log x because this is double logarithm and n is a constant. So we get a contradiction. If there will be only n prime numbers, then any large x can be described much shorter than the number of bits in the usual description. So the complexity of most x will be much smaller than its length if we switch to binary strings instead of integers. So x is arbitrary integer and binary description of x is arbitrary string. So we have a way to make a shorter description of every bit, every string. And this, as we discussed, is impossible. Most of them are incompressible. So the random number will have many prime factors. So this is a kind of proof. And actually, probably you can say that it's just cheating because we just counted the number of integers which can be represented in this form and show that they are much less than the number of all integers. But that's exactly what I want to say. So there is an informal, the same argument can be expressed in different languages, which somehow differ by logarithm. We can speak about number of objects, or we can speak of number of bits needed to describe the object. And the second is the logarithm of the first one. But you see that sometimes it's more easy to deal with formulas to count things like this. So this is our first example. So, yeah?
Can you prove something like a prime number distribution theorem?
No. No, I will say if you can prove it by counting, then I probably can translate this proof to a language of complexity, of Kolmogorov complexity. But of course, in this case, you can get some estimates from this, but this will be the same weak estimate you can get from counting in this way. So you cannot. This prime distribution is not very, very far away from what we can achieve in this way. Okay. So are there any questions about this argument? So please raise your yeah.
Probably just to clarify, if you want to prove the same theorem, but like in a normal way.
In a normal way.
What do you estimate?
Okay. Imagine that there are only n. Let me just repeat the proof in standard counting language. Imagine we have only n prime numbers. Then we want to estimate the total number of all integers less than some n. These integers can be represented in the form p1, k1, pn, kn, when ki are less than log n. So there are log n, let's say we have log n possibilities for the first k1, and we have log n possibilities for the second k1. So we have just log n. This is n times. So the number of integers which are less than n and representable in this way is just log n in the n, and this is much smaller than the total number of integers, which is n. So this is before taking logarithms, and our equality here was with logarithms. So we have just exactly n log x, and here we have log x.
Yes, so let me just ask another catastrophically stupid question. So one language is counting. So usually another way of proving the same thing by counting is just to take something random.
Counting is so I say that there is a bit information theory. There is counting. And they are different by logarithm, by taking logarithm, the translation. And the switching from counting to probability is just dividing by the number of total objects, total number of all objects.
Well, you mean in this case,
And in this case also, we can take a random string, a random integer between 1 and n, and count the probability of what is the probability that it has this form, can be represented as this product. So it will be we should divide everything by n. So then it will be probability. But okay, but no. So is this argument clear or okay? Just raise your hands if you are satisfied with this. Okay, and then just because you asked about probability, let me show another example, and then we can even show all three languages, and you will see that they are exactly the same. So this is also a very standard example of probabilistic method, which is called, imagine we have a matrix made of zeros and ones. And we look for a minor so we select some rows and select some columns, and want to have a matrix where in these rows and columns are on the same value. So either 0, 0, or 1 minor, constant minor. And the question is, imagine we want to avoid them. So we want to have no, I don't know, k times k minors. And the question is, of course, for k is 1, it's impossible. And for k is 2, it's possible only if our matrix is not large enough. N is not too large. And the question is, how large should be n? Or in other terms, if we have a fixed n, and we want to avoid as big minors as possible, well, how can we do this? Yeah, it's a kind of Ramsey. So we would just no, it's not necessarily symmetric matrix actually, but still we have and we have to make different choices in rows and columns. So it's not exactly, it's like a bipartite Ramsey thing or whatever.
So n is a number of ones.
And it's just the size of matrix. So we have n times n, we look for n times n matrix with no k times k constant minors. And the question is, when it's possible for a given n, how large can be the k? And the claim is that there is an k is O of log n. It's possible. So you can find n times n matrix without k times k uniform minors. So, the argument, let me start with probabilistic argument. Probabilistic argument just says that we took something at random, and a random n times n matrix has no uniform, I don't know how to say that, uniform constant minor with high probability, or has a minor with small probability. Okay, so just tell me how you will estimate this. So let's n and k be fixed, and how we will estimate the probability. So number of places when we can look for a minor times the probability to see a uniform minor in a given place. So what is the number of places? So we should select k rows and k columns. Now, if we want to be, let's not small n, let's be not to go into complicated computation. So this is rows and columns. And so then the probability of seeing a minor in a given place. This is 2, because there are 2, 0 or 1, and then is 2 to the minus k square, if I don't mix anything. Okay, so it will be more or less 2, it will be 2 log n minus k square. Yeah? Or something is wrong here.
Some k is missing. 2k log n.
2k log n, sorry. 2k log n, thanks. Okay, so let's take, for example, k equal to, I don't know, if we take 3 log n, what we have? We will have 6 log square n minus 9 log square n. So it's much less than 1 in this case. So in most matrices do not have uniform minors for this combination of. Okay, and then it's probabilistic argument. I guess you all see what we should say in terms of not probability but computation, counting. It's just trivial formulation. So we have the number of matrices is 2 to the n times n. It's number of all matrices. And the number of uniform matrices is just 2 to the matrices which have a minor is the same n times k, n times k. And here, instead of probability, we should write just the number of things which are just n square minus k square. This is how many positions are outside the minor. So you see that this is just exactly the same argument with this factor here and here. So probability in counting is just exactly the same thing. When probability is more important as a language? When we speak about independence of things. Because when we speak about counting, the intuitive idea of independence is lost. So probability is very useful here. And then to make the things, to make the parallel complete, so how we say complexity argument. So you can just, you don't need to learn the theory of Kolmogorov complexity. You can just understand this kind of intuitive way to explain the counting argument. So let's show that a matrix with a uniform minor, with a constant minor, is compressible, can be described shorter than just specifying all its bits. Can be described in less than n times n bits as usual description requires. Okay, so how will you describe a matrix with a constant minor? You probably can guess this. So what do you do? So we write the positions of columns. Each of them, there are k columns. So we need a log n bit for each column. And there is also the same number of rows. And then we need to specify what? For 1 bit, just 1 bit, it's a 0 or 1. It is a minor. And then we know all the elements of the minor. We need to specify all the remaining elements. Just, for example, in standard ordering, just leaving the places for, we know already where the columns are and rows are, so we can just leave the places for a minor, and which is n square minus k square bits. Sorry?
Maybe we should use the logarithm of k.
Okay, it's fixed.
Oh, so the question is, do we need to also to specify k? Yeah. In a sense, yes. But if we, for example, if we want to prove something for this specific threshold, like 3 log n, then we don't need it specified separately. It's just determined by everything. But anyway, this k will be such a minor thing compared to all the other stuff, so you can add it also. And so just when it's less than n square, when just this k square advantage is bigger than this is disadvantage. So log n times k plus 1 should be less than k square. And so again we get 2 log n k. Yeah. I'm cheating here. And no, there was 2. Of course, there was 2 log n k. No, so you see that I am just saying the same things in different languages, but actually this is exactly the same argument, and there is nothing no additional added value. It's just that I am trying not to not to show something non-trivial, but just to learn the language. It's like a Rosetta Stone. It's useful to make the same thing, say the same thing in different languages, so you can see how they are translated to each other. So this is example of Kolmogorov complexity argument. And then I can also give another example when the statement becomes more natural, or somehow the statement is also contains some information, complexity. This is a very old result of middle 60s, that if one tape Turing machine has a very difficult time copying things. So imagine that we have some string x, which is written on the tape and with some I don't know, separators, and our machine wants to, and there is nothing else on the tape, and our machine wants to get a copy of x here. So you can do it in n square if x is of length n. You can do it of n square steps. You just take something, take the first bit and move it, keep it in your head and move it to this position, and then you come back for the second bit, and then you move it here, and then you come for the third bit, and so on. So you need to make n moves. Each time you take one bit on distance n cells. So you need to, this trivial algorithm is n square, proportional to n square. So I don't know, is it clear what is Turing machine, what is tape, or we should go in more details how it's? Who think that Turing machines are clear and no explanations are needed? Okay. So yeah, of course, if the machine has another tape, then it will be stupid to bring things one by one, because you have a very powerful tool. You can copy all the things on the other tape and then move the tape to the beginning, and then switch to the other mode and copy from the other tape to the first one tape. And it's everybody who makes this copy and paste operation knows this quite well. So as it was said, when mathematicians started to use computers, they were all often confused with different interface things. And we found a way in Moscow, in Independent University, there was a special computer class, and usually mathematicians came there in the beginning of 90s and asked questions, how to do this or how to do that, or what is happening, and so on. And so we make a very important explanation. Then when you make a copy operation with one of the button of the mouse, you can put everything what you see on the screen in the mouse. And then we put another button, and the contents of the mouse is put on the screen back. This was a very clear idea. And then this metaphor was very useful for mathematicians. But still, here you use the second tape instead of the mouse. You put it there and then put it back. But there is a result which says that there is no way which can do it better for any other, for any string x. So can you see, for example, that for some strings x, it's possible to make copy faster? So we don't claim that every string requires n squared time. So how can you copy some string faster? Yeah.
You can just count them and remember it.
Yeah. So if the string is all zeros or something very easy to compute, then we can just check that our left just make a preliminary attempt, checking that this string is of this form. And if yes, we switch to the second part and we copy, regenerate this string. So it will be n log n for some x. But it's not possible to do it for all x's. Okay, and so please tell me who remembers the argument, why it cannot, not just know the argument, why we cannot be faster for all possible strings. So the time needed to copy the most unfortunate string is proportional to n squared. So who knows this? Okay, so it's good that many of you don't know this, because probably then we will appreciate Kolmogorov complexity argument, because it's very simple no, maybe I will be not completely formal, but at least the idea should be clear. And let's say a different complexity version, which is kind of a stronger version of this. Imagine that we have just a kind of, we are pioneers on the frontier of nothing. So we have some, here on the tape, we have something, we don't, anything. And there is a zone, initially the rest of the rest is empty. And our goal is to write something non-trivial here. So this is the zone, so there is kind of n size n distance, and this is a zone which is interesting for us. And we want to estimate complexity of the string in this zone after t steps. And we want to show that this is bounded by O of t divided by n. It's just a kind, like a physical thing. Imagine we have a kind of we want to bring not the information, but I don't know, some water. And here we have the infinite amount of water, and we want to bring the water in this region. And there is a kind of, our Turing machine now has not the head, but it just has some barrel for the water. And it can fill it here and put it here. So, of course, we need to bring something for each barrel brought from this zone to this zone. We need to make n steps. Yeah?
Please draw an arrow from where to where.
So here, source of water or information. And here is the information place when we should put. No, I don't know, target, not sink, but target. And of course, it's just a computation which is clear for everybody who. So if you have only one if your capacity is bounded, and the number of efforts is proportional to the distance you need to move things. Okay, so the complexity of the string is this zone is bounded by t divided by n. And so we forget about water and we switch to information thing. So how we bound this complexity? We need to describe somehow what will be in this zone. So we need some description of what will happen in this zone. And let me say how we can describe it. Imagine then we create a kind of boundary. So there was iron curtain between the world and Soviet Union. So just we are interested what is brought, what information crosses this boundary. So there is a kind of a police who checks in which state your head is when you go abroad. So, and this police person makes a record. States of Turing machine while crossing from left to right. So so we don't write down anything else, just the state of the machine. So if a machine crosses the boundary in some state, we fix the state, and that's all. And there is a crucial remark, which probably you can guess now. So what is this remark?
The number of Turing machine states is constant.
Yeah, number of Turing machine states is constant. This is one half of the remark. Actually, there's another half. So knowing the states, what we can do? We can reconstruct all the history of the world on the right of the boundary. So something is happening in this communist region, and we don't, being outside, we don't worry what they do and what is happening. But we are interested in what they bring. And this is enough to reconstruct everything, because we can just, initially it was empty. So we know the first state. We just put the machine in this state and let it do whatever it wants. At some point it goes back, and then for us it's lost. But then we know that at some point it comes back again, and with some other state. So we can compute whatever happens from this state. And so this is enough to reconstruct the contents of the tape on the right. So what we see, that the complexity of our final copied thing, complexity of this, not copied, just complexity of target, is bounded by some constant, which is how many bits we need to write down one state, times the number of crossings. Or in other words, the number of crossings is greater than complexity of target divided by some constant c. And now this is true for every position of our border post. And so if for every position we need that many crossings, that total number of steps, because of course at each moment we can cross only one border, the total number of steps is greater than complexity of t times this n. So is it okay? There is a bad thing, because t is not good. And so we get what we wanted. The complexity is bounded by time divided by n and a constant. So if to copy a string of maximal complexity, we need time proportional to its length. Times this distance, and of course we can the distance to reduce our initial question. Imagine that our string was like this. It was just zeros on the left and something complex on the right. And then we need to have these complex things on the right. So we need to bring n over 2 bits of information by distance n over 2. So Even to copy the right half of the string, we need something proportional to n square. Okay, so is it clear or not? Sorry? I didn't get it. Say it again. And oh, so could it be the upper bound? No, the upper bound will mean that of course n square is an upper n times the length is the upper bound, but for copying, or I'm answering the wrong question. Just say it louder.
Complexity of time less than c times number of operations.
Yeah, this one. Not crossing, but okay. This one. Yeah. So what is the question? So why inequalities holds? Okay. No, this inequality means that number of steps is greater than complexity times n. And so number of crossing at every point is greater than complexity, because this crossings information determines the target string. And number of steps is just the sum of number of crossings. So there are n places of crossings. And so if at each place we need complexity, at least complexity times the number of crossings at least complexity, then the total number of steps is just complexity times the length of the water this gap. No, it seems. No, maybe if you can ask again, maybe somebody else can answer, because it's something trivial, but I just didn't find the correct words to answer. Oops, no, it's a pity that. No, there is some kind of cheating also, because we didn't count it all the constant. We need to know also where is the crossing. So we need some additional information where the crossing position is, but they are just small things compared to the rest. And if you do it carefully, you will get this. Oh, okay.
Why we don't pay attention of the length of the water of the source? I mean,
Oh, so you say that we can get a better bound because actually this information should be taken from some far away. Yeah. Yeah. We don't worry about constants. We just want to have something proportional to n square. So we just artificially make this kind of gap and follow only the information flow across this gap. It's lower bound.
I didn't mean that gap, the previous picture. Yeah, well, the left where it is written source of water.
Yeah.
We don't pay attention of its length, right?
Yeah. So what?
Consider it is a constant.
No. It can be arbitrarily large. No. We have a.
But I think if we want to copy some bit that is larger than that is much larger, we should cross some path. No?
So you mean that we should go rather far away to get some non-trivial information, but this will only increase our number of steps.
Okay. So we copy only the last one.
Yeah, of course.
The rightest one.
No. We do whatever. No, in informal argument, there is informal metaphor and formal argument. In formal argument, we look at of the traces of what is carried across any border here, and we never put the border outside the gap. So in this formal argument, we just completely ignore what is happening on the left of this, and still each of them determines the target, so we can find a bound for the complexity of the target, or in other direction, bound for the number of crossings here, and
So we don't need to go later, right?
No, in our argument, we completely ignore this part of, of things. But if we return to our water metaphor, it's very clear. Of course, if you have just a water which is distributed evenly here, it's more difficult than if we have an infinite source of water here. But of course, it's only more difficult. So we are, but this part of the task is ignored. But still we need to, even whatever the water is, wherever the water is, we need to carry it across the gap. So this is unavoidable, and we count only this part of the work. Okay, so I am afraid to ask, but who thinks that this argument is convincing? Not very good. Better, but okay. Maybe somebody can ask something, because. See, can you ask again? Because I see that I mixed something very simple. It's trivial, so something I said just in the wrong way, or it sounds clear that it's even not possible to ask anything. Okay, so what should we do then?
What is the goal, first of all? We need to copy some complicated part of word into the gap, after the gap.
So the first original task was to copy the string. And we just show that not the copying the string, but creating a complicated string on the right, in some zone, initially empty zone, requires a lot of steps. So it's just a special case of copying, because if we copy a complicated string, we will have a complicated second half. So even this more general task is difficult.
So N it is a gap where easiest part of the word plays.
No, okay. Maybe what I did wrong. I used the n in different ways. So actually, n is a half. Here n is a half of original one. So when we initial problem of so initially we need to make a copy of string here and here to here. So this was our initial task. And then we consider special case of this. It was n. And then we consider a special case when the string is, this part is complex or incompressible or random. And then if we copy it correctly, and this is, for example, 0, and then if we are able to copy it, then we will have these complex things here. So our special, if we can copy things, we can at least create complicated things on some distance n over 2. We can create thing of complexity n over 2 on distance n over 2. No, yeah. So then we say that there is a general thing. If we have initially an empty tape and whatever we want here, then to create a complex object of, if we need to create an object of complexity, I don't know, m on size s, we need complexity m and size s, we need at least omega of ms steps. So it's general bound. If we need to fill something with m bits, and this something is s bits, s cells away from where the information is, then we need the number of ms steps. And so we apply this special thing when m is s n over 2 and s is n over 2. So we get proportional to n square steps. Yeah, so this is how things are related to. Okay, so maybe we should make a break now. Our plan is to have two more theorems, at least or one of these two things. We can look at lowest local lemma. Probably we'll do it first due to popular demand. And if there will be time, I will also try to consider Shannon coding theorem, which relates Shannon entropy and Kolmogorov complexity. This is just the curve which I tried to draw yesterday, that where the complexity of typical string is related, is near its Shannon entropy.